Swayam Prabha. Digital India. Educated India.
Welcome back. Now, this is a case study from the Great Run of Kutch in Gujarat, Western India. And this part is important because this area or the region which falls away from the one of the most seismically active region, that is Himalayan belt, sitting almost like 1,000 kilometers away. But nevertheless, it is close to one of the active fault system in the west, that is Chaman fault system. So we will discuss more when we get into the more details of this. The photograph which has been shown here is from Dholavira, which is one of the very famous ancient Harappan site, and people have linked this also to the Indus Valley civilization. So why Kutch is so active and why Kutch need to be understood in terms of the deformation pattern and the earthquakes which are occurring there. So as I told that this area is falling almost away from the Himalayan belt over here, but close to one of the fault system which is the again part of the Himalayan orogeny, that is Chaman fault system. And this part is your Makran subduction zone, which has also triggered tsunamis in the past in 325 BC. Another one was in 1945. Now Kutch region here, which is a very small one, but has triggered a couple of earthquakes. So if you go back into the history, so far what we have based on the records, historical records, and the geological or paleoseismic studies, we know that there were earthquakes in 893, then 1668, 1819, 1845, 1956, and then 2001. The 1956 was 6.1, whereas the other earthquakes, if you see, they are all greater than 7, or they are greater than 7.5. And then, as I told, that there were two major subduction zone earthquake along Makran subduction zone, sitting in west of this region, where we had an tsunami event in 325 BC, another one 1945. This part I will not discuss, but yes, it is important to be taken up here that there was an earthquake in Latur in 1993. The magnitude was 6.2. Now, based on this earthquakes, what we have discussed in Himalaya, the Himalayan zone is sitting in 5, and also the Kutch, which is quite unusual to see that the small patch of the land here or the region in this whole Indian subcontinent is sitting in zone 5, and this is because of the area has experienced large magnitude damaging earthquakes in the past. This event of 1819, which was been named as Allaband fault or Allaband earthquake, which occurred on the Allaband fault, was quite unusual in terms of the damage as well as the landscape which got changed after the event. If you look at the overall geomorphic and tectonic framework of Kutch region, then what we see is that very beautiful boundary here. There is a geomorphic boundary between the Thar, and this side we are having the marshy land. So I will quickly go into the details with what we have done in this area. Now this is an area which is sitting quite away from the main seismic belt, that is Himalayan arc, and Kutch is sitting somewhere over here. It's quite far off. Nevertheless, it is close to the Chaman fault system, which has been shown here, and then another subduction zone, the Makran subduction zone. Now, if we take the zonation map of India, then you will find that the Himalayan belt is in zone 5, pockets of Himalayan belt, and then we are having northeast sitting in zone 5, then Andaman Nicobar. We can understand that this part is sitting in zone 5 is because they are either close to the subduction zone, and this is your collision zone. Now, why this Kutch, which is sitting so far and very small piece of land as compared to which we take in proportionate to the Indian subcontinent, is having in zone 5, and why we are having so many earthquakes? So, when we started working here, we asked several questions to ourselves, but to some extent we were not able to get the complete all answers to our questions. Now, if you look at the historical earthquake in this region, it goes back into like there was earthquake in 1890 AD somewhere, and then there was again, this was greater than 7.5. Then we have following earthquake 1668. Then you have another earthquake in 1819. Then 1845, 1950, 56. Then we have 2001. This was 6.1, whereas rest are all greater than 7.5 but less than 8. Now, if we consider this earthquakes or the data which we have based on the historical chronicles or the geological signatures, definitely there is a reason why we have put this in zone 5. So, here there are listed a few Indus. There is an Indus earthquake 1668 7.8, 1819 Alaband earthquake which took place along the Alaband fault here, and then we are having another 1845 which was along this one, but this is again, as I told, that this is probably is a less one, but it is earthquake which has been recorded here. And this was 1956. The magnitude was not as high as 1819 and 2001. 2001 was in 7.6 magnitude earthquake. So this was less, actually it was not 8 or 7.5 magnitude earthquake in 1845, but this was bigger one. This was quite. So what we did was that I'm not going to talk about this event, but we have like very good signatures of this event resulting into the change in the landscape, and a river which used to flow through this, that river got disrupted. So this river used to come here and then used to flow through the Kori Creek, but now we don't see that river. So probably this was the event 1819 which disrupted the channel of Nara. So that Nara channel, which is tributary of Indus, used to flow through Kori Creek along back. So whether that we can correlate that disruption purely to 1819 earthquake, or there were earthquake in the past which also in a sense affected the change in the landscape over here. Now Alaband, I'll just tell a small story here, that the Alaband event was been named after the earthquake, because it resulted into the, we are not very sure that the 1819 earthquake was alone responsible for the disruption of the channel which flowed through this area and through Kori Creek getting into the Arabian Sea. But now at present we don't see this channel anymore. Now the story behind this is that the Alaband, how the Alaband name came up. So this says the Band of Allah. So in here there is a beautiful pond which got created after the displacement which was experienced on Alaband fault. So the land, if you take the cross section over here, then what you see is that the area has been uplifted and back tilted. So the river was flowing through this, got dammed up. So this is what they call as an Allah's Band. So this is known as Allah Band. So naturally Band of Allah, which resulted into the disruption of the channel. So no water is flowing across this uplifted area. Now our aim was to understand that what exactly has happened in the past, whether these are the only faults which are available, or there are more faults, active faults in this region. So after 2001 Bhuj earthquake, what we noticed was that there were a lot of swarm of earthquakes which have been triggered in this area. Of course, this was the rupture area, hence one can expect the aftershocks in this region. But at the same time, what we saw is that there were few earthquakes with magnitude 5.6 which took place in 2006 along the Gedi fault, and then so in particularly this region. Now this rupture is in the area where another fault which lies is known as South Wagad fault. So we were interested in knowing that whether there is a seismic loading which probably has taken place similar to what we see in Himalayas in Kutch region also. So because of this event which occurred in between the Kutch mainland fault and the South Wagad fault, whether this will trigger another event on South Wagad fault or not, and whether the South Wagad fault is an active fault or not. So this was also one aim of our study, that whether the South Wagad fault is active, that was in question, and how many paleo earthquakes have been triggered along South Wagad fault, if at all there were events in this region. So we started doing some detailed studies on these two faults, that is the Gedi fault and the South Wagad fault. So in total, if you look at what we see is that in last 500 years, Kutch experienced several earthquakes with magnitude 6 greater than equal to 6 and less than equal to 7.8. And these earthquakes are, as I was talking about, some of them are listed here. It is 1668 Indus Delta earthquake, 1819 Alaband, 1956, and then 2001. And then historical data also suggests that there were large magnitude earthquake in 800 to 1000 BC. And our study what suggests that the active fault studies from Kutch mainland reveal that major faults, mainly Katrol Hill fault and the Kutch mainland faults, have ruptured in during the Quaternary period, or maybe you can say in the recent time, displacing the Quaternary succession. Now these faults are sitting somewhere here. This is Katrol Hill fault and this is Kutch mainland fault. So these are the two faults which are also active and which have triggered the earthquakes in the past. We have practically done the active fault topographic studies along the Katrol Hill fault, Kutch mainland fault, South Wagad fault, Gedi fault, and Alaband fault. And from our interpretations, what we suggest is that all these faults, starting from the this is south to the north, all these faults you are having Katrol Hill Fault, Kutch Mainland Fault, then you are having South Wagad Fault, Gedi Fault, Island Belt Fault we haven't studied in detail. Then we are having Alaban Fault. All these faults are active and can produce large magnitude earthquake in near future. Now the question comes is that what happened in 2001? 2001 did not rupture up to the surface. So this suggests that probably the earthquakes which have ruptured the surface might be larger than 7.7 earthquake. I am taking the magnitude of 2001. So we can infer that the next events which are going to occur along this active faults must be larger than this one. So this poses a lot of questions in our mind, that what will happen in next 100 years or in recent coming years on along these faults actually. So this is the topography what we have in the South Wagad, but one thing which I would like to just make it a little bit clear quickly, that if you take the cross section like this, okay, and say this is north, this is south, then what we see in terms of the faulting pattern is, we have, like, if you start from south, then of course we have the coastal region here, then we have a landmass over here, the hills, okay, and then we have, so this is your south, so we have like this, okay, and then it goes like this, another one, then we have in between the South Wagad fault and the Gedi fault. In between we have basin here, and then we have the Island Belt fault is something like that, and then we have the Alaban fault. So Alaban fault is like that, like this here, but still people are having different postulations for this or this thing. So this we are having, this is your Alaban fault, which is so otherwise what I can do is I can put another slide and try to explain you this one. If you start from south, then we have this, then we go like that, then we have an Gedi, South Wagad and Gedi fault, then we have an Island Belt fault, and then we have this one is Alaban fault. So this is your south, this is your north. So you are having these faults are going like that, okay, movement along the fault, this is coming up here like this is coming up like that, then the Island Belt fault, and this is Alaban fault. So this is your Alaban fault, this one is your Island Belt fault, and this is your Gedi fault, this one is South Wagad fault, and this one here you are having the Bunny basin, and this one is your Kutch mainland fault, is your Katrol Hill fault. So we have a configuration of the oppositely dipping faults. Now this has happened basically because of the inversion tectonics. Now you might be thinking that why I'm putting so much of geological and tectonic portion talking here, because for hazard analysis we also need to understand that what is the depth of the fault and which side the fault is dipping, because as we discussed in the previous lecture about the hanging wall and footwall. So if you are having this as a reverse fault, maybe I can draw very much similar. For example, if you are drawing Alaban fault, then we have this block is moving up with respect to this one. Okay. So this will be your hanging wall, this will be your footwall. And in a simpler way, the hanging wall which will move during an earthquake will have higher ground acceleration. And if the earthquake is triggered here, this will be your focus, this will be your epicenter here. Earthquake will not take place here because there is no fault over here. So this is, for example, if we take this is your north, this is your south, then this is with the scenario with the north dipping faults. But the scenario will be different for the south dipping faults. Okay. So if you are having the thrust fault which is moved like that, okay, then this is your hanging wall and this is your footwall. So the things will differ from if you have the different. So when we talk about the hazard scenario in Kutch, we need to be extremely careful that which fault we are talking about and what is the configuration of the faulting in that sense. Okay. So this was in short what I want, and then this is applicable everywhere or wherever you are studying the fault. So what is the depth, in which direction it is dipping? So that is important for us. So if you look at this part here, like the south Wagad, okay, then what we see is that so we have south Wagad which is showing the scarp facing towards south, and the Kutch mainland fault is showing the scarp which is facing toward north. So if we quickly take the cross section here, what we see is that we have from north to south, then we have north which goes like that, and then we are having the basin, and then we are having the Kutch mainland. So these faults are dipping on either side. This is your north, this is your south, and this is your south Wagad fault, and this is your Kutch mainland fault. So the geology or which you see here is that we are having the Mesozoic and the Quaternary cover. Similarly over here and here also we are having Mesozoic, and partly we also see the tertiary rocks. Geomorphologically, if you look at, then we are having a chain of islands. This is on Khadir Island, and on Khadir Island this hosts the famous Harappan site, that is Dholavira, and then we have Bela Island, Chorar Island, and then Wagad Island, and this is connected or with the Kutch mainland as a part of small basin which is known as Banni or Samkhali Basin. So we did detailed study and mapping of the faults and the geomorphic landforms which are attached or are associated with this, and we identified a very prominent site in terms of the active fault scarp, and then dug the trench, tried to look at the paleo earthquake history from this area. So I'll quickly take you like through the field which we did from Mahe area right up to the Shivlakha area, and very quickly show you that what is. Now one thing which you can easily make out is that these are the structures, the geological structures which you can see here are all what we call anticlines, okay. And then in some locations what we see is the elongated anticlines, okay. And the arrows which are been shown here are the arrows of the movement of the anticlines. So whenever there will be a rupture, there will be an addition of the length here as well as it will gain the height. Similarly, this is the plunging anticline which is moving in both directions, and so if this anticlines keep moving towards one like in either direction, lateral movement, what we say during during different earthquakes, the time will come it will link up, and these are the linkage segments which have been shown here. So in Himalaya also, if you look at, we are having a smaller folds like this, and like but the time will come then this folds will get linked up, giving rise to a larger fold segments. So these are moving in this direction, this side notch is moving here like this. This is what similar phenomena of deformation we observed in even Kutch. So this will be a sort of a linkage area which has been shown here. This is the linkage point of two segments, and slowly this will grow. This also testifies that yes, of course, there is a movement which has been experienced by South Wagad fault in the past. So this was another important finding. So we are just not jumping directly saying that okay, this is an active fault and this is hazardous or not, but we are also taking into consideration that what has happened in the past and similar things can or the process will prevail in future also, and for sure that this region or the South Wagad fault must have hosted large magnitude earthquake in the past, very much similar to or must be probably greater than what we experienced in 2001 Bhuj earthquake. These are the examples which we see, or the signatures which we see in the deformed areas, and these are the old rocks, tertiary rocks which have been folded, and this is the scarp at Mahe anticline which I was showing in the previous slide over here. This is the area at the Mahe anticline, and then further we are moving to the next one, that is close to Vamka. We see an uplifted terrace. So South Wagad fault which we have marked is running over here actually. So if you open up the section across this, you will be able to see the displacement. So these are the evidence of that. So this area, if you take the profile, then it looks something like that. So this uplift was not in the single event, but this was resulted into by multiple events or multiple earthquakes, and the height which we see here from this top up to the base here, okay, is your cumulative height. So multiple earthquakes. So again it proves that this area has experienced earthquake in the past. Okay. This is another example of fault scarps which were observed further ahead near Halera, and then we also looked at that small streams which are just having a few kilometers of the basin area or the watershed area have incised the region or the area, like it shows deep incision. This is again an indication of sudden land level change because, or the base level change because of the uplift. You can see the incision of more than 2.5 meter or so, and another features which we see is the formation of the terraces along the river valley. Then in one place where we found that this is the most was the most prominent area to open up the trench. If you see the Google picture here, this is the eastern nose of Adhoy anticline, which I was showing in the previous slide. So this is the fold which is propagating in this direction. Now, taking an advantage of what we did in Himalaya, we also applied here, because this is again is an example of fold and thrust belt, very much similar to Himalaya, but this is on miniature scale. This is not at the magnitude what we see in terms of the region. Okay, the towering height of Himalaya, if you see here in Kutch, is not the same, but yes, of course, I say that this is on the miniature scale. So we applied the similar technique or the methods to identify the best site for trenching. So this is Adhoy anticline, which you see here, where we identified the site, and this was the section which we encountered in one of the artificially dug trench by local people for agricultural or irrigation purposes. Okay. So we found that there is an evidence of very young displacement in very young deposits, and we decided that we will open up the trench here to identify the paleo earthquakes which have occurred during the historic times. So what I can do is I'll stop here, and we'll continue in the next lecture and try to discuss more about the interesting things about the South Wagad fault, and then we will also like to see whether the South Wagad fault was responsible in whether it was a damaging earthquake or it was just an earthquake which did not affect the region. Okay. Thank you so much.